In this video, we'll understand sequence models, recurrent neural networks, and LSTMs in a simple step-by-step way. We'll also look at common RNN architectures and test your understanding with short quizzes in between. Sequence models are machine learning models designed for data where order matters. This can be text, audio, video frames, or time series values. In these problems, either the input is a sequence, the output is a sequence, or sometimes both are sequences. Let's see a few applications. In speech recognition, an audio sequence is converted into a text sequence. In sentiment classification, a sequence of words is mapped to one label, like positive or negative. In video activity recognition, the input is a sequence of frames, and the model predicts the activity happening in the clip. A recurrent neural network, or RNN, is a deep learning architecture specially designed for sequential data. Its key idea is internal memory. That means it can use information from earlier time steps while processing the current one. This makes RNNs very useful in NLP and also in time series prediction tasks. Now let us look at this in a simple table format. RNNV, SLSTM. Main difference in memory handling. Here is the main comparison to remember. A traditional RNN is simpler, but it struggles with long-range dependencies because of vanishing gradients. LSTM improves this by adding a cell state and gates, which help preserve useful information for a longer time. Unlike standard neural networks, RNNs share weights across time steps. This is important because the same transformation is applied as the sequence moves forward. Also, RNNs can remember previous inputs, while standard feed-forward networks do not naturally keep that history. So RNNs are better suited when past context matters. Now that we've covered sequence basics, let's test what we've learned so far. Here's quiz number 1. See if you can get it right. Question 1. Which type of data is best suited for sequence models? The correct answer is ordered data. Sequence models are designed for data where order matters, such as text, audio, video frames, and time series. Question 2. Which is a common use of an RNN? The correct answer is natural language processing. RNNs are widely used in NLP because language is naturally sequential. Question 3. What is a key advantage of RNNs over standard neural networks? The correct answer is they remember previous inputs. RNNs maintain internal memory, which helps them use historical information while processing sequences. In an RNN, the loss is often defined using contributions from multiple time steps. During training, backpropagation happens through time, meaning the model is updated by tracing how errors flow across the sequence. So learning depends not only on one input but on how the full sequence unfolds. RNNs can be arranged in different input-output patterns. One-to-many means one input gives a sequence output, like image captioning. Many-to-one means a sequence input gives one output, like sentiment classification. Many-to-many can map a sequence to another sequence, either with equal length or different length outputs. Let's connect those patterns with examples. Image captioning is one-to-many because one image leads to many words. Sentiment classification is many-to-one because many words lead to one class label. Machine translation is many-to-many because one sentence is converted into another sentence and the lengths may be different. Now that we've covered RNN structures, let's test what we've learned so far. Here's quiz number 2. See if you can get it right. Question 1. Which architecture is used in sentiment classification? The correct answer is many-to-one. Sentiment classification takes a sequence of words as input and produces one output label. Question 2. Which task is a good example of one-to-many architecture? The correct answer is image captioning. Image captioning starts with one image and generates a sequence of words. Question 3. What is true about many-to-many RNNs? The correct answer is input and output can both be sequences. Many-to-many architectures are used when both input and output are sequences, such as named entity recognition and machine translation. Traditional RNNs are not very good at learning long-range dependencies. The main reason is the vanishing gradient problem. As gradients are propagated back through many steps, they can become extremely small. When that happens, weight updates become weak, and the network struggles to learn from faraway context. LSTM, or long short-term memory, was introduced to overcome this issue. It modifies the hidden layer by adding a cell state that carries information forward. Then it uses gates to control what to forget, what to add, and what to output. This allows the model to keep important information for much longer. The forget gate removes information that is no longer useful. The input gate adds new useful information into the cell state. The output gate controls what information should be passed forward as the output. This gating mechanism is the reason LSTMs are much better at handling long-term dependencies. Now that we've covered LSTM memory, let's test what we've learned so far. Here's quiz number 3. See if you can get it right. Question 1. What main problem does LSTM address in traditional RNNs? The correct answer is vanishing gradient problem. LSTM was introduced to help RNNs learn long-range dependencies by reducing the impact of vanishing gradients. Question 2. Which extra component does LSTM carry across time steps? The correct answer is cell state. In addition to the hidden state, LSTM passes a cell state through time to preserve important information. Question 3. Which gate removes information that is no longer useful? The correct answer is forget gate. The forget gate decides what information should be discarded from the cell state. Nice work! You now have a solid understanding of sequence models, RNNs, and LSTMs. If you want, I can also convert this topic into a shorter revision video or a slide-by-slide classroom version.